The story of Gilbert Lewis is a fantastically interesting one. He was an American physical chemist who is actually credited with the discovery of the covalent bond and the very concept of electron pairs. His so-called Lewis dot structures have shaped almost all of our modern theories of bonding in organic chemistry. Though he was nominated an astounding 41 times, he sadly never won a Nobel Prize. But many think this was because of a feud between him and several members of the Nobel Committee. Though he never won a Nobel, he actually mentored several other chemists who eventually did, putting Berkeley on the map as one of the world's most prestigious centers for studying chemistry. As if the Nobel snub wasn't enough, even his death was shrouded in controversy. He was found dead on March 23, 1946, in his laboratory after working with hydrogen cyanide, and many postulated that his cause of death was suicide. You can read up on Gilbert Lewis online, but for now, let's learn about Lewis dot structures. So how do we use Lewis's ideas to help us envision what molecules might actually look like? Let's start with the Lewis rules for drawing these Lewis structures. I've listed 5 of them here, and you could write them in any number of different ways, but this will suffice for our purposes today. What these rules are meant to do is actually quite powerful. What we should be able to do by the end of this class is to give or look at any generic chemical formula, at least simple ones, and to be able to infer how these atoms must be connected. And we're going to use ideas about electrons, ideas about valence orbital structures of elements to try and piece this all together. And so here are the rules that I recommend for doing this. First thing you want to do is actually add up the valence electrons that you have, and be sure to adjust the number in case you have any ionic species, because we should be able to handle ions with this process just as well as neutral species. So if I look at this particular structure, I see that I've got a carbon atom. And when I look at the periodic table, for carbon, I can see that carbon is located here in the periodic table, and to count valence electrons for these elements is relatively straightforward. You're looking for those elements in that highest principal quantum number, which generally correspond to the row, right? So if I look at where carbon is, it is 1, 2, 3, 4 elements into the second row. That means it'll have 4 electrons in its highest principal quantum number orbitals. And so I would say that it's got 4 valence electrons. That's the key here. Now, if I go back to my periodic table and I look for oxygen, which is the other element I have to take care of in this particular structure, I can do the same argument. And I can say 1, 2, 3, 4, 5, 6. In other words, I would say that my oxygen atom has 6 valence electrons. And now what I'm going to do here is I'm actually going to adjust those numbers because I have to take into account how many of each type of atom I have. Notice I only have 1 carbon atom in this structure, but I've got 2 oxygen atoms. So taking that into account, 4 times 1 atom gives me a grand total of 4, whereas 6 times 2 atoms gives me a grand total of 12. And if I add both of those together, I have a total of 16 valence electrons to take care of in this particular structure. That means that in the bonding in this carbon dioxide molecule really needs to involve 16 different electrons. Okay, so that's rule number 1 done at this point. Rule number 2 says write the atomic symbols for the central atoms, or central atom, and connect all of the outer atoms. In this particular case, this structure is not so challenging. There's only 3 atoms anyway, but let me talk you through maybe some of the more reliable ways to find what the central atom is in most of these structures. So a central atom is generally written first. Not always, but generally written first. And so when you see these various polyatomic species that you'll have to imagine how they're bonded together in a Lewis type way, generally what we write first is the central atom. And in this case, that is certainly true. So what we'll do is we will write the atomic symbol for that element that is the central atom, which is the carbon. We'll write that first. The other thing we might notice, just using reasonable, logical arguments, is that there are 2 oxygen atoms, but only 1 carbon atom. So it would be difficult for one of these oxygen atoms to be the central atom, and we would somehow have to put a carbon and another oxygen around it. We might not write the formula like this if oxygen happened to be the central atom. So that's another aspect to keep track of. Now, rule number 2 says write the symbols for the central atom and then connect all of the outer atoms. So what I'm going to do here is I'm just going to write my other atoms, my other oxygens, on either side of my carbon atom here. And at this point, no, there is no specific reason why I would have written them on either side of the carbon atom. I've just done that for symmetry reasons here. But at this point, had you written those oxygen atoms in some other place, so far that's actually fine. We'll discover some more robust rules a little bit later to help us clean these kinds of things up, but for now, this is perfectly valid. And that actually satisfies rule number 2. Rule number 3 says we are going to complete octets around our outer atoms. So what does an octet mean? This is a new phrase for us in this particular course, although I'm sure you've heard of the term octet before in high school or in other chemistry courses. An octet is not a word I'm particularly fond of, but the rationale or where the word octet comes from is this notion of 8 electrons. And that is really just a circumstance of the periodic table. If I look at the periodic table, at least the top half of it, let's do that for now, I notice that there are 1, 2, 3, 4, 5, 6, 7, 8. 8 elements across the top of the periodic table. And we know from last class that 8 electrons in the highest principal quantum number orbitals of all of these elements is an exceptionally stable thing, don't we? We saw all kinds of evidence for that. So it seems like when you fill up your s and p orbitals, you create a very stable arrangement. And that is actually the driving force behind creating bonds in the first place. Elements who don't otherwise have that full set of s and p orbitals can now borrow electrons from other elements to get the full set of s and p orbitals and get stability by sharing electrons with other atoms rather than rely on having those electrons all to themselves. So what do we do with this information? Let's go back to our structure that's in progress. Octets is this notion of giving 8 electrons to elements because we know that that's a particularly stable arrangement. Not for all elements, but for the vast majority we deal with. So we want to complete these octets. First things first, though, let's look at the structure we have at the moment and realize that so far, right, connecting these outer atoms, at a minimum, we need to connect all of our atoms. That is at the very least what we're going to do. So we're going to indicate those connections with these straight lines. And this was an invention, a human invention to sort of indicate how atoms were bonded. And what these lines correspond to, according to Lewis, is 2 electrons, right? So this is this notion of sharing bonds, or sharing electrons rather. And so to indicate that this oxygen atom is bonded to this carbon atom, I'm going to draw a straight line between them. And that straight line represents 2 electrons, one from the carbon atom and one from the oxygen atom being shared. Okay. Now I'm not finished with my electronic Lewis structure quite yet, but what I should do just to keep an accurate tally of my electrons is realize that I had a grand total of 16 electrons, and so far I've just placed 2 here and 2 here. That's a total of 4. And so in terms of the additional electrons that I have left to account for, there are still 12 left. And why that's relevant is that in this particular rule, I need to complete these so-called octets around my outer atoms. So, according to Lewis, basically what we do is we have 4 sides to an atom. This is really just a counting exercise. And what Lewis often does is place electrons and dots on each of those 4 sides. This is not something to be rigorously adhered to. The point is really only that we want to complete octets around these outer atoms. So if we remember that this bond corresponds to 2 electrons that this oxygen atom is sharing, that means there are 6 more electrons that I can give this oxygen atom. So I can place those as dots in the vicinity around this oxygen atom. I've placed a couple of dots on the top, on the side, and then on the bottom. I can do the same with the oxygen atom on the other side. So there we go. I've placed 6 dots all around the outside of this atom, which gives a grand total of 8 electrons that that atom has access to. Each of the 6 dots that I've indicated, as well as the 2 in the bond between it and the central carbon atom. Now, if I tally all this up, I've added 6 electrons over here and 6 electrons over here. That's a grand total of 12. And so if I am keeping track of my tally, and I'll slide that over here, then I can realize that I've actually just allocated all of the electrons. So all of the electrons that I tallied in the first step of this process have now been accounted for, and they're all inside this diagram. So with that, my rule number 3 is complete. Rule number 4 says place any leftover electrons on the central atom. Well, in this particular case, I don't have any leftover electrons, so there's nothing left for me to do for rule 4. So I can check that one off as being satisfied as well. Which brings me to the 5th and final rule, which says if a central atom doesn't have an octet, try multiple bonds. Now, those of you who know how to do this will almost immediately see that this looks like a strange carbon. And the reason it looks strange is because it doesn't have an octet. Carbon is one of the elements in the periodic table that we almost always see with an octet. In other words, we see it with 8 electrons in its vicinity. Now right here I've got 2, right here I've got 2 more, but that's only a grand total of 4 in the vicinity of this carbon atom. So I need to find a way to give it more electrons, even though I don't have any more to add to this diagram. This is why the rule is suggesting that I try multiple bonds. What does it mean to try multiple bonds? It means to shift electrons around from your diagram to satisfy the element that doesn't have an octet. And so here's one thing I can do. I can notice that I've got a pair of electrons right here on the oxygen atom. Okay. Now I have many other pairs. It is arbitrary that I'm choosing this one to talk about right now, but I can see it there. If I were to drag that pair of electrons between the carbon and the oxygen atom, that would be like saying, well, I'm going to take this so-called lone pair, right? That's what we would normally refer to as a pair of electrons placed in the vicinity of an atom in a Lewis structure. I'm going to take this lone pair and I'm going to actually consider that it's a bond, right? And so we can do that. So let's take that pair of electrons. I'm going to erase it from there. And what I'm going to do is I'm going to add that pair of electrons as an additional bond. So notice I've not changed the amount of electrons at all. I've just taken 2 that were in one place and moved it to a bond between that place and the next atom. Now that's totally okay to do because you'll notice that I actually haven't changed the electron count of the oxygen atom. Now there are 4 electrons tied up in lone pairs, and there are also 4 more electrons tied up in 2 bonds between that oxygen atom and the central carbon atom. Therefore, my oxygen still has an octet, which is why shifting lone pairs into the interbonding region of 2 atoms is a good idea to try and satisfy the octet of a neighboring atom that has less than enough. Now, once I do that, I notice that my carbon atom now has 6 electrons, and it's probably a good idea to do it again. But doing it again with the same oxygen atom, not always a great idea, for reasons I'll talk about in a moment. Generally, we try to be as symmetrical as possible in these cases, and so if I want to do this again, it's best to choose an electron pair on the other oxygen atom. So what I'll do now is take that pair, move it inside as another bond, and now I can notice that both of my oxygen atoms still have their octets as they always did, and now so does my carbon atom. So just these relatively simple electron counting rules, these 5 rules that I've gone through so far today, can help me rationalize the fact that the carbon monoxide molecule probably has very strong bonds between the carbon and the oxygen atom. In fact, they're probably double bonds. And I can reason that simply by counting electrons, thinking about orbitals and stabilities due to things like octets, and just manipulating where those electrons are such that all of my atoms are in a state that I believe is probably the most stable. So we haven't even really scratched the surface in terms of all the different things we can do with the Lewis structure yet, but at the very least, we learn what is the most likely arrangement of atoms and how they are most likely to be connected. All right, so when we were putting this Lewis structure together, you'll recall that we had a choice to make, and potentially that may have seemed like an arbitrary choice to you. And what I want to do right now is introduce a concept called formal charge. Okay, so this is not explicitly a charge on our molecule or on any of the atoms. I'm not talking about charged species. I'm talking about a concept known as formal charge that helps us make decisions when putting together Lewis structures. And now that was a decision that I had made more or less intuitively on the previous slide. And what I want to do now is talk you through that in a little bit more detail. You'll remember we had a structure like this when we were almost done. And what we had done was we had taken this electron pair right here, this lone pair, and we had placed it into the bonding region between carbon and oxygen to rationalize that we would have had 2 double bonds, one on either side of the carbon atom. That may have seemed a little bit arbitrary, and so what I'd like to do now is introduce the concept of a formal charge to help us understand or explain how we would make a better choice, or how we'd make the optimal choice of what to do. And the reason why we need to do this is, let me make a copy here. There we go. What I want to do now is actually try both different options, right? Let's try the 2 options and see what we get. First of all, we can remember what we had done in the first place is we had drawn that electron in the double bond region to create the following molecule. We had oxygen with 2 lone pairs, 2 bonds, a double bond to carbon, and then the same thing on the other side of the molecule. Now, just to be clear, there is no significance to writing these lone pairs on the side or on the bottom. We could write those lone pairs really wherever we want. And this was the result of doing this particular change. And this is nice because all of our elements have octets. Now, let's be clear though, there isn't technically anything wrong with us potentially having chosen one of those lone pairs. We could have chosen the same oxygen to pull lone pairs from to create our eventual molecule. Had we done that, what we would have been left with is the following structure. An oxygen singly bonded to a carbon atom, and then a triple bond to another oxygen atom with a lone pair left over. Now, if I'm counting octets, one of the things I'll notice is that all of my atoms are still satisfied in the structure on the right. I've got 6 electrons in lone pairs, and I've got 2 electrons in a bond. That gives this oxygen atom an octet, total of 8. Same can be said for carbon here, where I've got 4 bonds in my vicinity, therefore I've got a total of 8 electrons. Likewise with this oxygen on the right, 2 electrons in a lone pair and 2 in each of these 3 bonds for a total of 6 here. 6 plus 2 makes 8. All of my atoms have octets, whether I write the structure like this or like this. But surely there's a correct answer, isn't there? Both of these structures will have obeyed the rules that we talked about before, and so I've got a bit of a decision to make. And what I'm here to tell you about is this formal charge, this concept of formal charge is what will help us make this decision. All right, so I'm going to slide my structures over and make a little table to help us think about this conceptually. Remember, I'm trying to evaluate the quality of both of these options that I could have gotten earlier. Now, the way I do that is I think about how many valence electrons did each of these elements have before I started to make a molecule with them. If you are having trouble with that, recall that that was actually our starting point over here. Carbon had 4, oxygen had 6. These are the valence electrons that these elements typically have. So I can make a note of that here in the tally that I'm about to make. My oxygen atoms have 6 valence electrons, and each of my carbon atoms have 4, and that's the same for either one of these structures. Now, the next question I have to ask is, in the structures I've drawn, how many electrons does each of these elements now own? I'm using that phrase owned as a contrast to the word shared in bonds, right? So I'm not talking about how many electrons do I currently have access to, because I know in that case that all of these elements have their octets, which is a total of 8. What I'd really like to know in this case is how many are owned by the electrons, or in other words, they have full ownership of. Let's take a look at this oxygen atom for starters. There are 4 electrons as lone pairs on that oxygen atom. That oxygen atom certainly owns all 4 of those electrons. But what about the bonds? Well, if we think of a bond as a pair of electrons being shared by 2 atoms, then we imagine that 1 electron in each of those bonds is owned by each atom. So this bond that would have 2 electrons in it essentially has one of those electrons that belongs to the oxygen and the other that belongs to the carbon. But the same can be said for the second bond. One of those electrons is owned by the oxygen, one is owned by the carbon. So that means that for each bond that I draw, there is 1 electron in it that belongs to each atom. So if I'm going to calculate how many electrons do I imagine this oxygen as owning, I would count 1, 2, 3, 4, 5, 6 in total. 1 for each of the lone pair electrons, and 1 for each of the bonds. Now the same exact thing can be said for this oxygen because it's a perfectly symmetrical structure. But let's continue on and look at these other oxygens. This is where the difference will come into play. This oxygen has 1, 2, 3, 4, 5, 6 electrons in lone pairs, and then only 1 bond. So it's got 7 in total that it has access to, which can be compared with this oxygen on this side, which only has 2 electrons in a lone pair, and 1 for each of these 3 bonds for a grand total of 5. Notice the difference. Now, if I look at my carbon atoms in both cases, they're essentially identical from an ownership perspective. If I own 1 electron in every bond, then each carbon atom has 4 bonds, and therefore each carbon atom has a total of 4 electrons that it owns. And so now the real question is, what is the formal charge on each of these elements, or each of these atoms in these structures? This is expressed as the difference between the top number and the bottom number. In other words, how many valence electrons does the atom typically have? Subtract how many electrons it has full ownership now of in this particular structure. And that will give you the resultant formal charge. So in this case, I can clearly see that all of the formal charges for the structure on the left equate to 0. 6 minus 6, 4 minus 4, and 6 minus 6. But on the right-hand side structure, I get 6 minus 7, which gives me a formal charge of minus 1 for this particular oxygen atom. Likewise, I've got 4 minus 4, but then 6 minus 5, in other words, a formal charge of plus 1 for the oxygen atom on the right. Typically on tests or exams, if we were writing out our formal charges on atoms and molecules, I would indicate these with small superscripts near the atoms of interest. And I could say that my formal charge on all of these atoms is indicated as such. The question, though, is how do I use these formal charges to make any sort of guesses about the stability of these various structures? Well, at the end of the day, the answer is simple. You want your formal charges to be as close to zero as possible. Now, it won't always be possible to make your formal charges zero, but if it is, formal charges of zero are always better than formal charges of not zero. And additionally, the larger the number of your formal charge, the worse it generally is. So if we were to have a structure that had, say, a -3 or 4 as a formal charge on a particular atom, that's a very unfavorable thing to do because it means that in the structure you've drawn, you've significantly changed the number of electrons that that atom has access to relative to its typical valence. So that's something to keep in mind. If you have two options, one of which having either non-zero formal charges or significantly large formal charges, compared to the other one, which is either zero or having relatively small formal charges, the answer is universally the one with the smaller or zero formal charges. All right, so we seem to have these rules about imagining how molecules can be constructed just by simple arguments of electrons and their valence, atoms and their valence electrons. And we can put this together, and if there are more than one option, we can often evaluate the quality of those options using notions like formal charge, which again makes sense. And now I want to push us towards thinking about an even broader scope of molecules, and in particular, exceptions to these octet rules. Should we always expect elements to adhere to this notion of an octet? Of course, the answer is no here, and I want to highlight a few pertinent examples. For example, number one, if your molecule has an odd number of electrons, then I think it's logical to conclude that there is no possible way to give all of your elements an octet. You can't do that with an odd number of electrons. Let me give you an example. Consider the nitrogen monoxide molecule, NO. Relatively simple, of course, but if I do the calculation, if I do the rules we talked about earlier, we know that nitrogen has 5 valence electrons. Again, by consulting a periodic table, you can discover that. Oxygen, as we saw before, has 6 valence electrons, so we have a grand total of 11 in this particular case. Note the odd number. So this isn't going to work no matter what we do if octets are our goal, but I'm here to tell you that octets don't need to be your goal. So all we need to do is just follow the rules as we've done before and see what we get. So for example, we don't need to worry too much about which of these elements is our central element because there's only 2, and we'll connect them. Connecting them accounts for 2 total electrons, and so if I'm keeping track of my tally, 11 minus 2 gives me 9 left to place around this particular system. So what I can do is I can go ahead and start placing those. Again, I don't know which is my outer or my central atom because it's kind of irrelevant, but I can place my 9 electrons. Typically, I'll place them like so. 1, 2, 3, 4, 5, 6, 7, 8, and then 9. Notice I've tried to make lone pairs in a way that is typical around these atoms because they're typical atoms in the second row of the periodic table. And now what I can do is, thinking about my rules, I ask myself, are my octets satisfied? Now, if I look at the nitrogen atom, I see I've got 2, 4, 6, 8, so the answer is yes. And if I look at my oxygen atom, 2, 4, 5, the answer is unfortunately no. So what I can do is consider multiple bonds, as we've done in the past. So suppose I were to move this electron pair into the bonding region. If I do that, I will be left with the following. So now I have a nitrogen that is doubly bonded to an oxygen atom, and if I count up all of my electrons, let's do that. 1, 2, 3, 4, 5, 6, 7, 8. That nitrogen is now satisfied. 1, 2, 3, 4, 5, 6, 7. That oxygen isn't satisfied so much, but I only have 11 electrons. So this isn't possible to fully give it an octet. What I could do, though, is consider formal charge arguments, because, of course, you could realize that I do have the option of switching which of these elements has the single electron. For example, I can take this single electron, migrate it to the nitrogen, take this pair and migrate it back. My choice of placing all of the remaining 9 electrons onto these 2 atoms was arbitrary. I chose to put 6 on nitrogen and then the remaining on oxygen. I could have done the other way around. So let's evaluate the quality of that choice. And we can do that by using arguments around formal charge. Now, to do formal charge, we recognize or we remember that nitrogen has 5 valence electrons. We know that from our calculation that we started here. In the current structure, it has access to 1, 2, 3, 4, 5, 6. So it owns, in other words, 6 electrons in this particular structure. So 5 minus 6 gives me a total of a formal charge of -1 on this nitrogen atom. The oxygen atom I can consider in the same exact way, 6 valence electrons, and I've got 1, 2, 3, 4, 5 electrons that it owns, more or less, in this structure. 6 minus 5 gives me a +1. And so my formal charges are not 0 in this particular case. So there's 2 things I learned from this. One is that maybe the other option would have been the good idea, right, to actually put all of my electrons on the oxygen, which we'll do in a moment. But the second thing, and this is a convenient example to illustrate this, when you have a negative formal charge directly adjacent to a positive one, then it's generally a good idea to shift electrons from this side over to that side. And that's exactly what will happen if I migrate one of these electrons over to pair with this one, right? Which is what I would have gotten had I put my original 6 here and remaining 3 over here. So let's take a look at that quickly if we can. So we had nitrogen, we had oxygen, we had a single bond, and now let's try the other alternative. 1, 2, 3, 4, 5, 6 electrons, 7, 8, 9. Okay. Again, I notice my octet now on nitrogen isn't satisfied, so I will move 2 of the electrons here into the bonding region. I do that, and that gives me the following structure. And now I can check octets and see that my oxygen is satisfied, but my nitrogen isn't. But again, there's an odd number of electrons, so there wasn't any hope of getting that to work out anyway. Again, nitrogen and oxygen both had 5 and 6 valence electrons respectively, and in the current structure, nitrogen owns 1, 2, 3, 4, 5. Look at that. So it had 5 valence, it currently owns 5, its formal charge is 0. Likewise, for oxygen, it had 6 valence electrons, 1, 2, 3, 4, 5, 6. It also owns 6 electrons in this particular structure, and there you go. So we've learned that we don't need the octet rule to always be adhered to, because there are certainly exceptions, and formal charge can still come to our rescue when there's some ambiguity in terms of which structure to choose. And this one is indeed our correct answer. All right, so we just saw an example of a molecule having less than an octet because we were essentially forced to do that. And then we were forced to do that because of the odd number of electrons. But we can sometimes have a less than an octet without being forced by an odd number of electrons, but instead being forced by some simple arguments around formal charge. Take the BF3 molecule, for example, an excellent example of this. If I go through my rules of making Lewis structures, again, the first element written is generally our central element, our central atom in the structure, and we would generally put the others around it. So this, it was starting to get a sense of how we might do this. But first things first, of course, let's actually tally our valence electrons. So boron, according to the periodic table, again, if I refer back to the periodic table, there's boron. And if I count through the periodic table in the same principal quantum number, which in this case is 2, I get 1, 2, 3. So boron has 3 valence electrons. Now, what about fluorine? So fluorine, again, if I go back to the periodic table, here we are, there's fluorine, 1, 2, 3, 4, 5, 6, 7. So fluorine would have 7 valence electrons. But let's not forget that I've only got 1 boron atom, but I have 3 fluorine atoms. So this gives me a subtotal of 3 for boron, but a subtotal of 21 for fluorine, giving me a grand total of 24 electrons that I have to place in this particular diagram, in this Lewis structure, if you will. So let's do that. We know that boron is going to have to be our central atom. That's essentially not negotiable. And if we attach our fluorine atoms to it, I'm just going to attach them like this. Again, there's no rhyme or reason in terms of precisely where I'm placing them, but I'm attaching the 3 of them like so. In order to do that, right, this is the minimum requirement. I have to at least have 3 bonds between these things. I can see that there'd be 2 electrons tied up in each one of these 3 bonds for a grand total of 6, which means that my new tally, 24 minus those 6, gives me 18 electrons left to place in this particular diagram. So I still have 18 electrons to place. And my rule says complete octets around the outer atoms first, according to my Lewis structure rules. So let's do that. Completing the octets can be done by this way, putting 2, 4, 6. That would complete the octet around that fluorine atom. 2, 4, 6 would complete the octet around that fluorine atom. 2, 4, 6 would complete the octet around that fluorine atom, and that's 6 times 3 if you're keeping track, which means that I've just spent all 18 of my remaining electrons and I've got none left. So I am now finished putting electrons into this diagram. It's possible that I might want to move them around, but so far I have no electrons left. Now, the other rule says if you don't have an octet on your central atom, you can try multiple bonds. And that's certainly something that you might have tried in this particular case. So for example, I can take these 2 electrons, or these 2, or really any 2, and put a double bond in one of these places. But before you do that, let's just take a look at formal charges, right? So formal charges, this is our way of figuring out quality of Lewis structures. So boron here has 3 valence electrons. How many electrons does it own in the current structure? Well, it owns 1 of each of those bonds. That's 3. 3 minus 3 is 0. The formal charge of my boron atom in this structure is 0, and don't forget that a 0 formal charge is a good thing. Now, if I do the same calculation for fluorine, fluorine has obviously 7 valence electrons, and in terms of what it owns in the current structure, all 3 fluorines look the same, and I've got 1, 2, 3, 4, 5, 6, and 1 in the bond makes 7. And lo and behold, I discover that the formal charge of each one of these fluorine atoms is also 0. In other words, I have a pretty good Lewis structure. There is no reason to go messing with it. If I take 2 electrons from this fluorine atom and put it in to create a double bond here, yes, it will complete the octet on boron, but it will disrupt my formal charges. And in fact, you can try this at home. You'll notice that boron becomes negative, fluorine becomes positive, and as I said before, whenever you have a negative next to a positive, you want to try to shift electrons back in the other direction, which would bring us right back to this structure again. It is possible to have less than an octet and to be stable. And boron is perfectly stable with that particular arrangement because it is the best set of formal charges, and this is a stable structure. All right, last example, I promise. We're continuing on with exceptions to the octet rule. The third one I want to highlight for you is we've seen a couple of cases with less than an octet. What about more than an octet? Can we have species that have more than an octet? I'll first warn you that this is the case that requires a little bit more thought. But let's start by thinking about this example molecule that I'm highlighting here, PCl5. So we've got some phosphorus and 5 chlorine atoms, okay? So if I do the normal thing and think about all the valence electrons I have for this species and tally them up, a phosphorus atom, and we can refer to a periodic table just to confirm this, there's phosphorus there. If I count to phosphorus along the n equals 3 level, I get 1, 2, 3, 4, 5, and therefore 5 valence electrons for the phosphorus atom. Chlorine is just like fluorine. They're both halogens, and there it is right there. It would have 1, 2, 3, 4, 5, 6, 7 valence electrons. Now, let's not forget that I've only got 1 phosphorus atom, but I've got 5 chlorine atoms. So let's take this into account. That gives me a subtotal of 5 valence electrons to account for with phosphorus, but it gives me a total of 35 electrons to account for with chlorine, for a grand total of 40 electrons. So what am I going to do with these? Well, I have to make my molecule. Let's start with my central atom, which again I hope is clear in this case. We generally write those central atoms first, and if you've only got 1 phosphorus but 5 chlorines, chances are that phosphorus is your central atom. So in order to make a structure, I think of putting phosphorus first, and then I think of putting 5 bonds around it. I'll just sort of do a star shape like that, and then I'll indicate all of my chlorines until I finish it up. There we go. So there's the 5 chlorines around my central phosphorus. And let's not forget, every single bond contains 2 electrons. And I've got 5 bonds for a total of 10 electrons. So what that's going to mean is from my grand total, I have to subtract 10, and I'm now left with 30 electrons to place in this diagram. So, proceeding in the same way that I've gone every other time, I will go around all of my outer atoms and fill up all of my octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. There we go. And don't forget that we actually only had 30 electrons left. So I've just spent all of them, and then this is the structure I'm finally left with. Let's take a look at this. Each of these chlorines is exactly the same, so let's just look at one at a time, or just one in total. I've got 6 electrons placed around it in lone pairs, and then I've got 2 tied up in the bond between it and the central atom. That's an octet. So each of these chlorines is, quote, satisfied from the perspective of an octet. But let's look at the inner atom, this phosphorus. Phosphorus now has 5 different bonds. If each one of those 5 bonds contains 2 electrons, that's 10. And I know that you know that 10 is greater than 8. So I violated my octet rule for this particular molecule. And I guess there's a couple of take-home messages here. One is that this is the correct structure, and yes, it's okay. But the second, which is probably the more important question that you should be asking yourself, and that is why? Why is this okay? We don't generally see this with other atoms in the periodic table. Let's take a look at a periodic table to try and explain this. Let's point out where phosphorus is, and it is right here. Notice it is in the 3rd row. That is key. What is special about the 3rd row of the periodic table? You're in the n equals 3 zone. And as you all will recall, the n equals 3 zone is the first point of the periodic table where you have orbitals that are called 3D, right? Now, are they populated? No, of course not. They're not populated at all. Here's the 3D block down here. But they are orbitals that are available. Right? Now, the other thing to think about is that as we go from the top down in the periodic table, our elements are getting larger, physically larger in space. We've just established that in a recent lecture. So as I am physically larger, I am physically more able to accommodate more bonds around me. So I've got a big size. I can fit 5 chlorines around me, but I also have nearby 3d orbitals, right? I have 3d orbitals that are accessible for electrons if I need to do that. Now, we haven't talked so much in this class yet about orbitals and how they dictate bonding. We've used some hand-wavy arguments about counting valence electrons, and we counted them based on principal quantum number, right? So the second row, we go across this way, the third row, we go across this way. But orbitals play a much stronger and much more prominent role in bonding than we've discussed till this point. And suffice to say, for this current argument, once you get to the third row of the periodic table, you have more orbitals near you that are able to accommodate more electrons. And those other electrons can come from other atoms. So if we look at our phosphorus pentachloride molecule here, chlorines, 5 of them are coming into the vicinity of this phosphorus, bringing a lot of electrons with them. Can phosphorus handle that? Can phosphorus accommodate all of those bonds? The periodic table tells us that it can, because it's in the third row and it has 3 d orbitals and 4 s orbitals just above its energy, ready to potentially contribute to a more complex bonding scenario. That is not possible for the n equals 2 level. The 3s is too much higher than the 2p set of orbitals. It isn't energetically worth it, and I can't actually bring more elements in my vicinity to bond to. So you will never see a structure like this with, say, nitrogen in the middle. It just isn't possible. Even though nitrogen is directly above phosphorus in the periodic table, and therefore you would expect to behave similarly, nitrogen just isn't big enough and just doesn't have enough orbitals in its arsenal to accommodate all of the electrons that it would need for an expanded octet. And so octets generally aren't broken all that often for elements in the second row and above. And these are very common elements: carbon, nitrogen, oxygen. We talk about these elements all the time. But as when you get down to the third row, you've got larger elements with more orbitals available and more complex bonding patterns also available. So keep a lookout for that. More than an octet is certainly possible so long as you're in the third row or below.